Hello, my name is Ayoub Afass and I will present my work entitled Wettability Effects on Homogeneous Cavitation Induced by Lead-Driven Flow. This work is supervised by Soufiane Derfoufi, Mohammed, Ahachad, Fatima, Bahraoui, and Mustapha, Mahdaoui. Solar water heating systems are an appealing way to implement an essential aspect of renewable energy, providing a direct conversion of solar radiation into thermal energy. Also, it's a solution to improve the energy efficiency of residential and commercial buildings through simple technology and short payback period. Solar water heating system can be customized to suit any application, on the basis of which the water loop can be fully operated through thermosiphon or by employing a pump to ensure water circulation. In the most high-efficient solar water heating system, pump often a fundamental component. Although it's a reliable tool to control the forced flow, yet its weakness to induce cavitation is a real issue. The cavitation is a desired phenomenon. It reduces pump performance by generating shock waves that can even destroy the pipeline. To grasp the effect of cavitation on the flow and the density field, this work presents a preliminary study on the bubble cavitation induced by the gravity and lead-driven flow by using the pseudo-potential lattice-Boltzmann method. Hence, the physical model is a square cavity filled by saturated water at 0.9 temperature of critical state. The fluid is under a gravitational acceleration of 10 to the power of -5, while the lead-driven flow is defined by Reynolds number of 200, and the working liquid is assumed to be Newtonian and incompressible. The lattice-Boltzmann method is used to resolve this physical model. Here, the two-step of conventional lattice-Boltzmann method is presented, collision and streaming, where F is the single particle distribution function. Here, the improved pseudo-potential lattice-Boltzmann method is presented, where F is the external force, including intermolecular, the adhesive, and the gravitational force. Then, the macroscopic properties such as density and velocity are obtained through the next equations. To validate the home code, the first step was to check it via the lead-driven flow test. The two figures present the velocity magnitude in the central axis. It can be seen that the presented result is in agreement with those presented in the literature. Then, the following step was to check the validity of the multi-phase flow. The Maxwell construction is the conventional method to do that. Its aim to measure the density of the coexisting phases at each temperature below the critical state. The result of lattice-Boltzmann simulation and Maxwell analytic solution is depicted here. As is clear view, the two plots are identical. To end up the validation stage, we check up the adhesive behavior of a bubble in contact with a wall. As the results show, our model is able to simulate a wide range of contact angles. After checking the home code validation, we can proceed with the results. The picture figure illustrates the density and flow field for different values of the wettability. In all cases, a vapor phase develops in the upper region of the cavity. However, there is a noticeable change in streamlines and the vapor volume in each case. Also, there is two vortices appear at the edge of the vapor phase, acting as a barricade against the searching vapor. Indeed, the left vortex is larger than the right one. Moreover, the streamlines are slightly distorted along the interface of the two phases. On the left side, the curve of the vapor phase generated as function of the contact angle. It's shown that the relationship between the two variables is linear, and we can conclude that the wettability impulses the formation of the vapor phase. On the right side, the figure illustrates the effect of cavitation on the velocity field. The two velocity components are plotted along the center line in the case of cavitation and without it. Once the cavitation occurs, the velocity magnitude decreases massively across the domain. This can be explained by the discontinuity of the streamline across the interface. In fact, the vapor phase was enabled to transmit its momentum to the liquid phase. At the end, we can conclude that the effect of wettability is studied, finding a linear correlation between the fraction of generated vapor phase and the wettability condition of the wall. Also, the presence of the cavitation reduced massively the velocity across the domain.